So let's discuss a problem from GATE 2021 physics. So this is from electromagnetic theory and this is related to the solenoid and the variation of vector potential with respect to R inside that solenoid and outside that solenoid. So here you can see the question. So consider a solenoid of length L. So it is a solenoid of length L and radius R, where R is much more less than length. That means we can imagine the solenoid like this. So it is very radius of the solenoid is very less compared to the length. So we can just think it has infinite solenoid of that is solenoid of infinite length like that. Steady current flows through the solenoid. The magnetic field is uniform inside the solenoid and zero outside. So here we can see the current flowing. So it is connected to a battery. So current, this is the direction of current flow. So the current would be moving in this manner. So it would be moving towards us and away from us like that, towards and away from us. So based on this we can say that a magnetic field is in along the axis. So as the current is circular, the magnetic field would be in the axial direction based on the right hand rule, thumb rule. So would be just like coming towards and moving away. So and it is said that magnetic field is uniform. That means it is same everywhere. So it is not exponential increasing or decreasing with respect to distance from the center of the solenoid. So it is just remaining uniform, same everywhere. In that is for inside the solenoid, and when coming to outside the solenoid it is 0. So this one we need to keep an eye on. So next, among the given options, choose the one that best represents the variation in the magnitude of vector potential. So they have given vector potential. So here you can see only phi vector potential in phi direction is there. In radial direction and z direction there is no vector potential, there is no such thing. So only in phi direction it is. So we need best represents the variation of magnitude of vector potential and z is equals to L by 2 as a function of radial distance in cylindrical coordinates. So vector potential as a function of radial distance. So in cylindrical coordinates we just need to find out the vector potential. So here we needed to find out how this vector potential varies with respect to distance. That means we need to draw a graph between a phi and r. So here you can see in the options there is a graph between a phi and r, and also it is given the useful information here, curl of vector in cylindrical coordinates. So in cylindrical coordinates how we can find the curl of a vector, so that also hint is given. So of course here we can use Stokes theorem. So these are the options. So we could use Stokes theorem here. So according to the question, they have given magnetic field is mu 0. So inside the solenoid it is uniform. That uniform value is this mu 0 Ni. So N is nothing but number of turns per unit length. So here it is having some certain number of turns the solenoid. So that is that. So inside this is the magnetic field inside, and outside it is 0 as given in the provided in the question. So now we need to find the magnitude of A. That means formula for A, how it is going with how it is going to vary with respect to distance, or that one we need to find out. So for that, so here we just take the surface integral of magnetic field. So this is the surface integral of magnetic field B dot ds, surface integral of B dot ds. So we know that B is nothing but curl A. Formula for B is nothing but curl A. In the place of B we replace with curl A. So next, A dot ds. But according to the Stokes theorem, we know that surface integral of curl of a vector is equals to line integral of that vector. So this surface integral of curl of that particular vector A is equals to line integral of that particular vector A. So this could be replaced with this. So finally what would become means surface integral of b dot ds is equals to yeah, that means closed integral line integral of a dot dl. So now here if we use Stokes theorem we don't need to find this curl a. So yeah, because of this calculation becomes easy. So now here b dot ds is there. So actually b is nothing but flux per unit area. So how much flux is there? That means electric lines of force, how many are there for unit area? So that is nothing but d. And b dot ds is nothing but for that entire area how much flux is there. That means that means it is nothing but product of b into a, like that. So here we know that b is uniform everywhere, that is nothing but mu 0 ni, and area is nothing but pi r square. So how much area we are taking? So here you can see. So in this solenoid, so which amount of area we are considering? So this at what particular distance? So actually this is the axis of the solenoid. So at particular distance r, actually the radius of the solenoid is capital R, but as we are finding it inside the solenoid, so r, so here small r is less than capital R. So from here we could have some particular area, so that is nothing but pi r square inside that solenoid. So that is the, so hence mu 0 ni into pi r square. So total flux how much is there? This is the flux for unit area. Actually b is flux, how much flux is present in unit area, that means 1 meter square 1 centimeter square, like that, but we need it for pi r square area. So this much area, so mu 0 ni into pi r square. So here if we see only, so what they have given 0 a5 0. So this was given in the question. That means the radial component and the z component are 0, so they don't exist, only phi component is existing. So here as there is a dot product, so whichever is existing only we need to take that only. So only phi with respect to direction of length in phi direction. That means this is just like, so this phi direction means in this circular manner. So in this wires, the direction of these wires, how they are, so like this, so in this circular manner, so that is nothing but phi. So along circular direction the length is nothing but 2 pi r. So that's why we have taken 2 pi r. So a phi is in circular direction and the length also we need to take in circular direction. So if a phi is circular and length is also circular, so angle between them both is 0, so cos 0. So that's why we are having here a phi into 2 pi r. So along the circular direction only it is existing. So hence a phi into 2 pi r, length of that particular circle, circle of radius r. That is a circumference of that particular circle of radius r. So that is the thing. So next, so if we do, so here we can see r would get cancelled, r and pi would get cancelled. So what would remain is a phi is also mu 0 ni r by 2, mu 0 ni r by 2. So that is nothing but, if we consider this all of them as constant, so if the current is constant, number of turns per unit length would be constant. So mu 0 is a constant, however. So finally we can see that a phi is directly proportional to r. So as the value of r increases, a phi increases. That means as the value of r goes on increasing in this manner, so number of magnetic flux, that means number of lines, magnetic field lines, they would get increased. So because of that a phi is going to increase inside the solenoid. We are talking about inside the solenoid. So inside that solenoid the graph between a phi and r would be like this. So as a phi increase, as r increases, EFI would also increase. So this is about inside the solenoid. So now we need to find out the same thing for outside the solenoid. So again we use the same formula that we have found, that which we have already derived. So based on this formula, so surface integral of P dot ds is also line integral of A dot dl. So here, as we are moving outside the solenoid, that means as here we have moved outside the solenoid, so we are just standing outside the solenoid, like, so we can say we are just standing outside the solenoid. So here, somewhere here, so it is covering this entire solenoid. That means solenoid is of radius capital R. So hence mu 0 ni into pi r square. So only in this solenoid the magnetic field lines exist, because magnetic field inside the solenoid is uniform and outside the solenoid is 0. So there are no magnetic field lines outside the solenoid. They are only lying inside the solenoid. So total magnetic field lines in that particular area is nothing but mu 0 ni into pi r square. That's it, within the radius of the solenoid. However, we are standing outside the solenoid at a particular distance r. We cannot write here as pi small r square, but we need to write only pi capital R square, because the field lines lying only here in this area, in this region inside the solenoid. This one is equals to A5 into 2 pi r. That is in circular direction it is A5 vector potential has given. In z direction and radial direction it is 0, however, and into 2 pi r, that is circle of that particular radius. So this is the circle. So as we are residing inside, outside, so here in this circular form we are going to get. So the circumference of the circle is nothing but 2 pi r at the particular distance r. So now pi would get cancelled, only that. So what would remain is mu 0 ni r square by 2r. So this is the thing which is remaining. So here this mu 0 ni and radius of the solenoid, if we keep constant, and 2 also if we keep aside, so finally we can see that A5 is inversely proportional to r. So outside the solenoid vector potential is inversely proportional to r. So for 1 by 1, if r is 1, 1 by 1, that is we would get 1. If r is 2, 1 by 2, that is 0.5. So if r is 3, we would get something like 0.33. So 1 by 3, these are 9 like that. So 0.3. Again 3 like that. So 1 by 4, 0.25, which would be going on decreasing. So like this, it is nearly reduced to half from here to here. So like that, like this graph you would get when it is outside the solenoid, A5 between r. So as r is going on increasing, A is going on decreasing. So the solution for this problem is, so this, so inside the solenoid it is directly proportional, Fi is directly proportional to r, and outside the solenoid it is just inversely proportional. So the correct answer for this question is C. So C is the correct answer. This is the solution for this problem. So thank you.